talk about the Landau operator and also the Landau-Fermi-Dirac operator. So for Landau-Fermi-Dirac, I will just write LFD. And let me write down the formulas for those two things. So let's start with the Landau operator. So if you look at the density of particles which have velocity v, then the so-called Landau operator that I will write as QL of f is an integral operator with a differential part, which write like this. So let's say we are, and we will still be for the rest of the talk in dimension 3. And here you put this quantity that I will call pi of v minus v star. And then you have f of v star gradient f of v minus f of v gradient f of v star. So you can see that you have some kind of symmetry in the operator. Here we put usually v in the gradient, but you can sort of forget it. It cannot be anything else. And here the pi, sorry, there is a then v minus v star to the gamma plus 2. And here pi is in fact the projector onto the orthogonal. So if you prefer, the component ij of pi is just delta ij minus zi zj divided by z square. So the formula which is here was first written down by Landau in the 30s. And it tells you the effect of the binary grazing collisions on a density of particles which have a certain velocity. In principle, it should be used for charged particles because then one can check that most collisions are indeed grazing. Grazing means that the velocities are changed very little during a collision. And the case of charged particles is the case in which gamma is minus 3 here in the formula. So you can wonder why we put gamma plus 2 and then just to say that this is minus 3. But actually this is done in order to be coherent with the theory of the Boltzmann equation. So the point is that though this is the most important case and maybe the only important case, actually the mathematicians have are used to consider parameters which are not only free. So this is only, let's say, for mathematicians. And they take usually gamma between minus 3 and 1 included or not. The reason for that is that somehow this can be obtained by formal asymptotics from Boltzmann collision kernel. And in Boltzmann collision kernel, it makes sense to take gamma in this range and even to take 1 actually. And so because there is this formal asymptotics, this can be seen as a model which, let's say, comes out of the Boltzmann equation for which those gammas have a meaning. Okay. So that is the Landau operator. And maybe I will not say too much about its structure, but I would just like to point out the fact that this is second order in derivatives. This is quadratic, and this is dimension 3, which is all those things are common with the Navier-Stokes incompressible Navier-Stokes equation. And actually, the analogy goes a little beyond those features, and we will see that a little more later. So this is for Landau. And the Landau-Fermi-Dirac operator is a correction which was introduced to take into account the effect of, let's say, quantum effects. And basically, you just sort of introduce the exclusion principle inside the equation because you're looking at fermions. Okay?
So it's not called Landau-Pauli-Dirac?
Should be. I mean, I suppose that Fermi-Dirac is just because the equilibrium is a Fermi-Dirac. But anyway, I did not invent the name, so I will not go with this. So I actually will write it like QLFD epsilon. And here epsilon is directly related to h bar, let's say. So it measures the amount of quantum effects that, that is put inside the operator. So it starts basically as a standard Landau operator. So you have the same beginning, but here you add something like this, and you do the same at the level of the symmetric term. So it will be like this. And now, in order for this operator to make sense, you have to suppose that f is between 0 and 1 over epsilon. Okay? So instead of just having that f is bigger than 0, now you suppose that you are in this interval, and then the operator makes sense.
This epsilon is a number or an operator?
No, it's a number. So here, epsilon is a number which is related to h bar, depending on the scaling that you take. And in principle, you should think of it as extremely small. So for electrons, if I remember, you can sort of write it in a non-dimensional way, and then you find that it's a 10 to the minus, maybe minus 10 or something like that. Anyway, it's extremely small in real physics. So that is the definition of the kernels, and of course you can see that when epsilon goes to 0, formally you go from the Landau-Fermi-Dirac towards the Landau. Okay. Now I would like to present, let's say, the weak form of those operators. Maybe I can do it this way. I hope it's possible to still read what is here.
The first row, yes.
That's all. Okay, so let me write on this one. Just put this here. So the weak form of the Landau-Fermi-Dirac operator is the following. So you take the operator, you multiply by a test function phi, okay, and you integrate. So as you can see, you can do a first integration by part, and you will get minus gradient phi on the inside the integral. And then you have all the rest So maybe better to keep it inside. So I do not put now the dependence of pi. And then you have all those things. Okay? And the point is that it's a good idea at this level to sort of symmetrize between V and V star. And if you do that, you see that since you have a minus here, basically this will be transformed in minus the same thing. And so when you now do the sum of this one with the one in which you have transformed V in V star, you will get exactly 1/2 of this quantity minus the same quantity taken at V star. So one way to write this is the following. This. You still have the V minus V star to the gamma plus 2. You still have the projector. And now, here it can be useful to put in factor f of v times 1 minus epsilon f times f of v star times 1 minus epsilon f of v star. So if you do that, you see that this will amount to divide this by this times this, and the same here. So let me write it. So you end up with gradient f of v over f of v 1 minus epsilon f of v, like this, minus the same quantity taken at point v star, and all of this is multiplied by f of v star 1 minus epsilon f of v 1 minus epsilon f of v star dv star. And this is actually the most useful weak form of the Landau-Fermi-Dirac operator. The reason for that is that first you can get quite easily the conservations which are associated with the operator, and also the entropy structure which is associated to the operator. So let's start with the conservations. So the question is, okay, let me first say that here pi is a projection. You can apply it on a vector, and then this means that you will do the scalar product with this vector here. And another way to do it is just to do to apply pi to this vector and do the scalar product here. Okay. So the question becomes, for which phi do you have that the projector applied to this quantity is equal to 0? So it's quite easy to see that if you take phi as a constant, this will be 0. If you take phi as a phi of v is equal to some component of v, this will be also 0 because the gradients will be constant, it will disappear. And finally, if you take phi of v is equal to modulus of v square over 2, then this becomes v minus v star, and you take the projector onto the orthogonal of this, and this also gives you 0. So, in other words, the operator is made in such a way that it conserves mass, momentum, and kinetic energy. Okay? So, if you take phi of v is equal to 1, any component of v, and v square over 2, you get that this quantity, so taken on y, vi, or v square over 2, is equal to 0. And those are conservation of mass, momentum and kinetic energy. So at this point, if you now think of the evolution equation associated to the operator, you see that it's enough to take functions for which the mass, the momentum, and the kinetic energy are fixed a priori. And the usual way to normalize those functions consists in supposing that, so from now on, we consider F such that the mass, momentum, and kinetic energy associated to F are 1, 0, and 3. So this is the usual normalization here. Okay? So from now on, we will only consider F, which are non-negative, and which, so between 0 and 1 over epsilon, to be precise, and which satisfy this. Also, up to doing a rotation, you can impose that the integral of f vi vj is equal to 0 if I is different from j. So, up to a rotation in the space of velocities, we will suppose that this quantity is equal to something which is 0 when I is different from j, and when I and j are equal, we will call it Ti, and this is sometimes called the directional temperature. And according to the third conservation here, you see that the sum of the three directional temperature is 3. So, yeah. Okay, those are numbers between 0 and 3, and the sum is 3. Okay, so this is for the conservations, but actually it was observed by Landau that it's really possible to obtain a nice entropy structure for this operator. Actually, so Landau observed it in the case epsilon equal to 0, but it's not extremely difficult to transfer it in the case when the quantum correction is taken into account. And it is really no surprise if you remember that these operators can be obtained formally as some asymptotics of the Boltzmann operator, for which the entropy structure has been known for now, I think, 150 years, or something like that. So the idea here is to introduce a phi which is related to f, and the definition of phi in the case with the quantum correction is that it is logarithm of f minus logarithm of 1 minus epsilon f. So why take phi like this in the weak form? It is because this is really the function which, once you take the gradient, gives you exactly gradient f divided by f times 1 minus epsilon f. Okay? And so, you see that taking phi in this way, you end up here with something in which you have this projector here, which is a matrix with eigenvalues 0 or 1. And this is applied on the same vector here. Okay, and so you get something here which is non-positive if you keep the minus which is in front. Okay, and this quantity is called the Landau-Fermi-Dirac entropy dissipation of the operator. So if you do that, you see that the quantity, which is called, so D is for dissipation, let's say, of F, which is given by 1/2 of the double integral of, so as you can see, you have V minus V star to the gamma plus 2. And here, let's say that pi acts as a quadratic form on the same vector, which is this quantity minus this quantity. So this is taken on this. And let me write it maybe a second time just to say that this is a quadratic form applied on this vector. Okay. So this is the entropy dissipation of the Landau-Fermi-Dirac equation. I have forgotten about, sorry, f of v, 1 minus epsilon f of v, f of v star, 1 minus epsilon f of v star, dv dv star. So it's like this. And the fact that this quantity is non-negative, this is Boltzmann's H theorem. Or, to be more precise, it's the first part of Boltzmann's H theorem. Okay? So this is really, if you follow the asymptotics, actually you start from a quantum version of Boltzmann operator, which is called sometimes Boltzmann-Nordheim or Wellin-Uhlenbeck. You go through the asymptotics, and actually the entropy dissipation that you have at the Boltzmann level becomes this at the level of the Landau-Fermi-Dirac equation.
Sorry.
Yeah.
So what's in the quantities again?
It's the same, just I was too lazy to write down it again. So this is actually the projector seen as a quadratic form applied on the same vector. Sorry for being so lazy. So next point is that actually it is maybe a better idea for computations to see this actually as so to forget about the 2 here and to see this as the cross product between V minus V star and this quantity. So it's a different way of writing the projector in which it does not appear explicitly anymore. Like this. And you put it to the square. And you still have all the rest. Okay, and now there is in the theory of, let's say, collisional kinetic theory, there is always a second part in Boltzmann's H theorem, and the second part should tell you that if the entropy dissipation is 0, then F should be an equilibrium of the equation, which is a Maxwellian in the non-quantum case, and which will be, according to the name of the equation, a Fermi-Dirac in this case, okay? So somehow I should be able to prove that if this quantity is equal to 0, then F is a Fermi-Dirac. So actually this computation is completely central to this talk, so I will do it seriously. And it will be done under the condition that F is different from 0 and 1 over epsilon. So if F can be 0 or 1 over epsilon, then you might end up with some degenerate Fermi-Dirac state, which could be something which is, let's say, a characteristic function of something. Okay? So let's suppose this, and let's try to show that if this is equal to 0, then F is a Fermi-Dirac. Okay? Then you can see immediately that this is exactly the condition for eliminating this part, which is strictly positive now. This is also strictly positive except if V is equal to V star. And you end up just with the fact that this quantity is equal to 0. Okay? So then you get that for all V and V star, or almost everywhere, you have this. You have this. Okay. So, let me rewrite this using coordinates. Okay. So the point is actually, the thing to do for once is not to keep this sort of factorized version, but to expand everything. So when you do that, you see that if you take I different from j, so coordinates between 1 and 3, then this is the same as looking at vi djf over f1 minus epsilon f taken at point v minus vj dif over f1 minus epsilon f at point v. So this comes from v times gradient f over f1 minus epsilon f. And then you have the same term, but taken at point v star. So something like this, plus now the same, but exchanging v and v star, like this. And finally, terms of the same kind, but in which you have only v star. It looks like a lot of terms, 8 of them. And the traditional proof, the one which is taken directly from the work of Boltzmann, consists in taking this and taking a sufficient number of derivatives in v and v star in order to eliminate as many terms as possible. So you can guess why this should work. It's really because in front of the terms of derivatives, you always have polynomials of degree 1 at most. So if you take 2 derivatives, it should give you 0. Okay? So if you do it in a clever way, you indeed end up with the fact that f will be a Fermi-Dirac thanks to this procedure. Of course, in principle, you should know that f is of class C2 if you are at the time of Boltzmann. But if you come with this idea after Schwarz, you can also do it in the sense of distributions, and actually it works. Okay? But the point is that actually, in analysis, there is one rule, which is that it's always better to integrate than to take derivatives. And so a much better idea turns out to be, instead of taking derivatives here, to really multiply by sort of the right multiplicator, to take the integral with respect to one of the variables, let's say v star, and to check what happens. So it turns out that the best multiplicator for this is to use this quantity here. So you multiply this thing by this quantity and you integrate with respect to V star only. Now, keep in mind that, well, of course it's not here anymore, but I hope you can see it here. Keep in mind that we made those hypotheses, which includes that the momentum is 0 for F, and you have that this integral is also 0 when I is different from J. Okay? So because of that, when you multiply with this, you see that this starts like the momentum. So if you take the first term here, actually the two first ones, then it will give you 0 because the momentum is just 0. So actually, this implies that in the formula here, you start with 0 plus 0, okay? Then you look at next one, the one which is here, and you see that it's like V star I times dj or something. You do the integration by part, you will take the j derivatives of V star I, this is also 0. Okay, so you will have 3 zeros. Then you look at the next one. Next one is so next one will give you something which is not 0. So let me write it. So it's just, so it's this one. Okay, it just gives you Vj times the integral of dif over 1 minus epsilon f taken at point V star times V star I. Okay. And you look at this one. So this one, you multiply by this, you see that in V star you end up with the directional temperature Ti. So it gives you Ti times this quantity here. djf.
Sorry, but in the third you have an F V star missing?
No, because you multiply by f of V star and you have the f.
Ah, sorry, I didn't see.
So it
that.
sort of cancels.
Yeah, I can see.
Usually I do it with the standard Landau. Okay. So here I may do some mistake. Okay. So now look at this one. This one you will multiply V star I by V star j, but you just use the fact that this is 0 when I is different from j. So it's 0 again. Then for this one, you have like V star I square, and here you have something which is a derivative with respect to j. When you do the integration by part, it will give you 0. So you still have yet another 0. And the final one tells you that you have here something in which V does not appear at all, and it gives you dif over 1 minus epsilon f taken at point V star times V star I, V star j. And all of this is equal to 0. Okay? So, are we better than previously? If you look at things, you see that somehow you have proven the following, that this quantity here is actually a linear combination of 1 and Vj. So finally, the integral of djf divided by f1 minus epsilon f of d is something that you can write down as aiv plus b. Okay? So the b would be this, and the ai would be this. You see that it depends on I. That's a strange thing, because you have here something which is the jth component, and it depends on I at this level. But you are in dimension 3. So actually, if it depends on I has to be different from j, but you can use the third dimension to say that it's the same as the ak, if you wish. And so actually this has to not depend on I. So there is a first argument which tells you that actually this thing does not depend on I. Sorry, there is no integral here. And there is a 1 here. So now what are the functions for which the J derivative is a first order polynomial in V? Those are exactly the Fermi-Dirac distributions, because this exactly tells you that the logarithm of f minus the logarithm of 1 minus epsilon f is this quantity once you have integrated, so a second order polynomial. So you end up with f Fermi-Dirac. And this is the second part of Boltzmann's H theorem. Okay, so at this level, let me say that somehow, if you now want to do analysis on those operators and on the evolution equation which is related to them, so I don't know if I use this, maybe. I will try not to use the. Okay. So now let's see what are the natural a priori estimates for the equation dtf is equal to q LFD epsilon of f. So you look at the evolution equation, sometimes called the spatially homogeneous Landau Fermi-Dirac equation, and you wonder what are the good a priori estimates. So the first thing is that thanks to the conservation which is written at this level, you see that you naturally have that d over dt of integral of f of tv times 1 vi v squared over 2 dv is equal to 0, which tells you that f will be in L infinity L1, 2, L1, 2 being L1 with 2 moments. Here this is a time variable, and here this is the V variable, okay? So this is the first natural a priori estimate. And then you have a second one which comes out of the entropy structure. So the one which is written here. And this can be written in the following way. So now you define the Fermi-Dirac style entropy. So this is just defined in the following way. So this is the integral of f log f. So it's better to put 1 over epsilon in front and to put epsilon everywhere inside. So this is log of epsilon f plus 1 minus epsilon 1 minus epsilon f of v times log of 1 minus epsilon f of v. So this is the Fermi-Dirac entropy. And you can check that if you now take a solution of the equation and you differentiate this quantity, then this will exactly give you the phi which was defined here times df over dt. So this is equal to the integral on R3 of log f of v minus log f of 1 minus epsilon f of v log of times df over dt dv. But df over dt is now q, and what we showed when we looked at the entropy structure is that this quantity is exactly the entropy dissipation, and it's of course the reason why it is called the entropy dissipation. Or to be precise, it is minus the entropy dissipation, which is here defined as non-negative. So let's write it like this. And this naturally gives you a new a priori estimate by integrating between time 0 and t. So what you end up with is the following. So S epsilon at time t is plus the integral from 0 to t of the entropy dissipation estimate is S epsilon at time 0. Now, S epsilon is not something which is really positive, but it is close to being positive. And so you have the natural entropy estimate, which is that this quantity is typically in L1 in time. Okay, so this tells you that D, LFD epsilon of F lies in L1 in time. Actually, it is even it's true on the compact set, but actually it is true on 0 infinity. So, then what is the point? The point is that you can try to extract from this something which is usable. So you would like to get some, I don't know, for example, a Sobolev norm out of this quantity. In order to do this, what you must do is to get some kind of inequality from below, from this quantity. So you should prove that this is bigger than some Sobolev norm of f. And actually, so let me write it maybe here. Try to write it here. So actually, I was able to prove a few years ago that in the case when epsilon equal to 0, so this is for the entropy dissipation of Landau, that dl of f is bigger than some constant times the integral of gradient of square root of f to the square. So this quantity is sometimes called the Fisher information, multiplied by some weight, which is related to the gamma which appears in the equation. So in the Coulomb case, this is really -3 that you get here. Minus something which is like, which is something that you completely control, which is related to, so I don't know, maybe there is a 2 here, but anyway, it's something which is controlled by the conservations. So, and here, the constant C, actually, it depends only on one thing. It depends only on an upper bound of the entropy itself, which in that case is S0 of F in the case of the Landau operator. So, what does this tell? Basically, it will tell you that because of this, you have an extra a priori estimate for the equation, at least in the Landau case, which is that now using a Sobolev embedding, okay, let's first say that square root of f is in L1 in time with value in H1 in V. I think it's L2 in time, H1 in V. So this is a direct consequence of this. Okay. And using a Sobolev embedding at this point, you end up, in fact, in L2 in time, L6 in V. So this is for square root of f. And if you write it for f itself, it tells you that you are in L1, L3. And actually, there is a weight here, which I will not write, which comes out of this. So it's a little less favorable with respect to the. So I would like to take.
Sorry, Laurent, the weight then depends on the gamma. So what you have for the Coulomb case for the weight is.
I think it's L3 minus 3 here, if I remember.
So it's negative.
It is negative anyway for the Coulomb case. So my point is that you are now in a situation which is close to what Maria described for the compressible Navier-Stokes equation. If you do the analogy that U looks like square root of f. Okay? So the square root of f, it is in L infinity with value in L2 because f lies here. Okay? And the gradient of the square root of f is in L2 in PV. Okay? So you have exactly, for square root of f, you have exactly the a priori estimates which appear in the Leray solutions. So because of this, actually, it's possible to prove for this equation, so for the Landau without the quantum correction, a lot of theorems which are analogous to what is known for the incompressible Navier-Stokes in dimension 3. So I don't want to say too much about this. Let me say that there is the equivalent of the Caffarelli-Cohn-Nirenberg, and this was proven quite recently by François together with Humbert, Gualdani, and Vasseur. There is the equivalent of the theorem by Leray, which tells you that if U times gradient U is small enough, then you have a strong, global strong solution for the incompressible Navier-Stokes. And also that for a time sufficiently large, all solutions become, all reasonable solutions become smooth. So this was proven 1 year ago by Lin Binghe, Jinchang Jiang, and myself. And hopefully there is also a prodyserine type criterion which works for the equation. This is not completely checked yet, but at least one case has been proven completely by Louis Sylvestre. Okay, so what I would like with a few minutes which remain is just to say one word about the proof of this and how it can be sort of extended to the quantum case. So the whole point is the following. Instead of looking at the case of equality in the equation, you say, well, let's look at this quantity. This quantity, I know that I control it, okay? I want to show that this is bigger than something. So what is the link between this quantity and the quantity which is here? Well, this is just the integral of this times the square of this quantity, okay? And this quantity is rewritten here, okay, in detail. So now if you want to get a quantitative estimate, the whole idea is to say, well, actually, let's replace 0 by something which I call Qij. And what I know is that the integral of Qij to the square times V minus V star to the gamma times F 1 minus epsilon F times the same at point V star. All of this is a quantity that I control, okay? So I know that I control this, I write this, and the point is, how can I get gradient F over something, so something which has to do with the gradient of F, out of this formula? And the whole point is to say, well, let's copy the proof of the case of equality, but keeping here the Qij instead of putting 0. So you do exactly this, and all the terms which are 0 remain 0, and the only thing that changes is that here, instead of having 0, you get the integral of Qij times V star I f of V star dV star. And in order to link this with this, you see that this is basically some kind of Cauchy-Schwarz inequality that you have to use. Okay? Because if you take the square of this quantity, here you will have a square, you will integrate in V, and then using some kind of Cauchy-Schwarz, you will end up with this. Okay? So at the end, the whole point is to follow precisely this proof of equality and to make it quantitative. So, if you do that, the question is, we know that it works for the Landau equation, but is it possible to sort of get the extension for the Landau Fermi-Dirac? And the answer, the recent answer, is yes. So, what I can say now in one word, maybe, is that it extends to Landau Fermi-Dirac. And this extension is uniform in epsilon. For epsilon small, okay, we don't look at large epsilon here. So you get something which is, you get an estimate like this one, which is uniform in epsilon and which basically gives you this estimate when epsilon is equal to 0. Then you might say, well, is it interesting to have such an estimate for the Landau Fermi-Dirac? Because for the Landau Fermi-Dirac, you already know that f is less than 1 over epsilon. So for a given epsilon, you already have an infinity a priori bound. And so is it interesting to know that you have some LP with p much less than infinity? And the answer is not so clear. But the whole point is that at least this enables to do the large time behavior of the equation and to show the following. that if you take now f at time t minus the Fermi-Dirac equilibrium, and you do that in L1 norm, this is less than C1 exponential minus C2t with C1 and C2 explicit for solutions of the Landau Fermi-Dirac. Unfortunately, this is not true for the physical case, which would be gamma equal to -3, but we know how to do it at least in the case when gamma is between 0 and 1. And this is not exponential, but close to exponential if gamma is between -2 and 0. We are still far from -3 in this. So that is the most recent, let's say, extension of those estimates, and maybe I will stop there.
Thank you, Laurent. Questions?
So what is the physical system Landau wanted to describe with that?
So it's a collision in a plasma, basically. So you have, so suppose, for example, that you know that the electrons are already thermalized, and you look at the equation for the ions. So you will write down df over dt equal to the Vlasov part, let's say Vlasov Maxwell, and you will add this Q of f with the right numerical constant in front in order to model the collisions between the electrons. Between the ions. There are a lot of problems related to that, but anyway, this was his idea in the 30s, and this is what is used currently in plasmas in which collisional effects are significant. So, for example, it's not the case of ITER, in which they say that collisions should not play any role. Mm-hmm.
So, for fermions, epsilon is 1 in physics, and for bosons, the Nordheim equation comes with epsilon equals -1.
Yeah, sure.
It looks like the conservation laws and the H theorem are not sensitive to sign of epsilon. Is that true? And can epsilon go to 0 from below?
Yeah, you're right. The whole point is then that if you look at the Bose-Einstein case, then there are a lot of new issues which pop up, like possibility of getting a condensate in finite times or things like that. My feeling is that if you avoid the formation of a condensate, which may happen in some instances, then probably you can go to a Bose-Einstein distribution with the same kind of exponential decay. But I don't think anybody did any serious, let's say, rigorous results in this direction. So it's a very nice question. Some people are working on the Boltzmann Bose-Einstein equation. I'm not sure that people have really been working on the Landau Bose-Einstein.
What's known about the regularity of Landau Fermi-Dirac in the Coulomb case?
Absolutely nothing.
Nothing. Even
so, I mean, if I'm not mistaken, even existence of weak solution is not known for a reason. Yeah. So, sorry, to be more precise, nothing is not which is uniform in epsilon. Let me be more precise.
Okay.
So, if you take a given epsilon, then you have solutions in L infinity, and then I think you can do everything. But all of this will not be uniform in epsilon.
But in that case, is it clear that L infinity implies regularity?
I think so. I'm not 100% sure, but I think so. I mean, all the work which has been done, by the way, I should say that this, the last part has been done together with Ricardo Alonso, Véronique Baglin, and Bertrand Lotz. And this group is really specialist of the Landau Fermi-Dirac, and they systematically look only for estimates which are epsilon uniform for epsilon small. That is, they are only looking for things which are still true when epsilon equal to 0. So you might wonder if taking the weak solution of the Landau equation that we have now, if it works for the Landau Fermi-Dirac. But the point is that in the Landau Fermi-Dirac you have cubic terms, and even for epsilon small, it's not so obvious to what to do with them. And for example, in both theories, you always need moments in L2 instead of moments in L1.
I see.
I mean, it's not a definitive argument, but anyway, it's not trivial that you can make solutions with estimates which are uniform in epsilon.
Yes.
Last question. So this is somehow like a consistency check. So when you're doing N-body dynamics for fermions, usually your L-infinity bounds come as for free. They just come from the boundedness of the operators. Whereas here it looks like it's a feature of the equation in the sense that if F0 is less or equal than 1 over epsilon, then you can actually propagate this L-infinity bound. Is that correct?
Yes.
So this is something that you have to prove. It doesn't come just for free.
Let's say if you, of course, I mean, if you want to derive the Landau Fermi-Dirac from n particle models, you will have a lot of troubles, and basically you can do it formally, not much more. But at least formally, you can check that the bound that you have ends up in the bound that f is less than 1 over epsilon. Now, if you forget completely about the n particles model, you can check that from the point of view of PDEs, you have a maximum principle for the Landau Fermi-Dirac when f is equal to 1 over epsilon. Basically, because you have always 1 minus epsilon f in the equation, which will be 0 when you reach 1 over epsilon.
So the maximum principle comes from the elliptic structure of the equation?
No. It really comes from the fact that you have 1 minus epsilon f in front of terms. No, because if it came from the elliptic, it will still be true when epsilon equal to 0, which is not the case.
Thank you.
Okay. Yes, please.
Just like partial regularity or so, is it extendable to epsilon positive?
Now, once again, if you take epsilon strictly positive, I think you know that this is regular.
Okay.
But the point is, would it be possible to do something which is uniform in epsilon for epsilon small? And then I don't know at all. I think that the theorem on partial regularity is quite recent, and so people have not seriously had the time to sort of adapt it. I see nothing in principle that would be a problem there, but one has to check.
Okay. Then if there are no other questions, we thank Laurent again.